In the last section, it was power series as functions 1. And the point of that section was really just to define what it meant for a power series to define a function and to discuss the domains of power series functions, which are the intervals of convergence of the power series. And the way we're going to, and then we looked at the ratio test and it told you effectively how you could find intervals of convergence except for possibly the endpoints. The ratio test gives you the radius of convergence in all the examples we looked at, but it won't tell you whether the series actually converges at the endpoints of the interval of convergence or not. And in general, we need to put off that kind of consideration until we have a lot more tests on infinite series. But it's not the main point of power series. The main point of defining functions as power series is that, okay, at least on the interior of the interval of convergence, so throwing away the endpoints, even if it converges there, power series functions behave like big polynomials or never-ending polynomials. And that's what we want to look at in this section. And let me just go ahead and get rid of the suspense. Power series functions are continuous, they're differentiable, and you differentiate them like they're big polynomials. They're integrable, and you integrate like they're big polynomials. You add, subtract, multiply, divide them like they're big polynomials. You substitute into them. It's power series functions are nice. They're just like never-ending polynomials, at least on the open intervals of convergence, so the interiors of the intervals of convergence, and that's what we want to look at today. All right, I guess I'll start with it. This sounds theoretical, and in fact, I'm trying to get the continuity, differentiability, and integrability out of the way first, because those are kind of the coolest things. So let me just state Abel's theorem. This is Abel's theorem. It's in a way it's a very theoretical thing, but it is useful at times. Abel's theorem: power series functions are continuous. And of course, continuous for a function means continuous on its domain. The domain of a power series is its interval of convergence. So are continuous, so you can say power series functions are continuous on their intervals of convergence. Now, I've said it, and I'm going to look at it more, that power series functions are actually differentiable on the interior of the interval of convergence, so where you maybe throw away the endpoints. Differentiability implies continuity. So the main content of this for us is that power series functions are continuous at the endpoints of the interval of convergence if the endpoints are there. So it's this gets said in different ways in different books. One of the points for us, or the main point, is that suppose for instance, suppose a power series converges on, let's say it converges on this. So I mean, in fact, I mean this is its interval of convergence. Suppose a power series has this for its interval of convergence. Of course, then the power series is centered at 0. Its radius of convergence is 1. Let's call it something p of x. Converges on this. And we know that on the open interval, from -1 to 1, p of x equals some continuous function f of x, some continuous function. continuous on at least this interval. But I'm really kind of thinking of continuous on the whole real line, but continuous function, so really I'll just say continuous on minus 1, 1. All right, what am I doing? I'm telling you how Abel's theorem typically gets used. You've got a power series. Somehow you know its interval of convergence, including possibly what happens at the endpoints. This means you have to know more tests than the ratio test, because the ratio test will never tell you what happens at the endpoints of the interval of convergence. And we know that that power series equals some function. Now I'm thinking of something like natural log of 1 plus x and the Maclaurin series for natural log of 1 plus x. And suppose you know they're equal on the open interval. Now there's we'll see later that you can get that in a nice, easy way by integrating. You get that they're equal on the open interval, and then the question is, why do they necessarily have to be equal on this half-open interval? Why do they have to be equal at the endpoint also? And, well, it's because both functions are continuous. The power series is continuous by Abel's theorem. You're assuming you've got some other function or some other function. It looks different. Some other function that is continuous on the same interval. And they're equal on the open interval. Well, that means that their limits would have to be, because they're equal on the open interval, the limit as x approaches 1 from the left of p of x would have to equal the limit as x approaches 1 from the left of f of x. But we're assuming these are f and p are continuous, so this is just f of 1, and p of x is continuous by Abel's theorem, so this is just p of 1. So of course they have to be equal at the endpoints also. The way this frequently gets said in textbooks is a little bad. They say things like, if a formula holds on the interior of the interval, then it holds at the endpoints if they're in the interval of convergence. Yeah, they need to be continuous, and if a formula holds, well, if the two functions are equal. But this is Abel's theorem. It's mainly of theoretical interest in that it can tell us when a formula is true at the endpoint, or at endpoints of the interval of convergence. All right, okay, that was exciting. Let's do something that we're not going to prove this or even have an idea of the proof. It's not particularly easy to show that limits of finite sums, in fact, are continuous. But something that is easy but very useful, is substituting into power series. Now, it looks like this would require a theorem, but it doesn't. So let's look at something like, I'll say it again, we're just trying to show that you can treat infinite series like they're big polynomials. So we know that e to the x is equal to its Maclaurin series. So as functions, we have this equality for all x. Now, if x is a number, x squared is just some number. So we could look at e to the, I guess if I want this to match what's into the book, 5x minus 1 cubed. So if x is some number, then x minus 1 is some number. X minus 1 cubed times 5. It's just some number. X here is just a real number, so we just replace this x by this number. I mean, this thing is a number for any particular x value. So as functions, we just put the 5 times x minus 1 cubed in for each x on each side. And you get 1 plus 5 times x minus 1 cubed plus, all right, if you put that in here, you'll get a plus a 5 squared over x minus 1. What did I left out a term. I was ignoring this one plus I was half ignoring it. You get a 5 squared and x minus 1 to the 6th over 2 factorial plus a 5 cubed plus x times x minus 1 to the 9th over 3 factorial, and so on. So you get this new power series centered at 1 for e to the x, for the function e raised to the 5 times x minus 1 cubed. This looks like it requires a theorem. It doesn't. This is true no matter what number x is. If x is a number here, all you've done is put in 5 times whatever that number is minus 1 cubed for x everywhere. So this power series does equal this as a function. What we don't know, and this requires a theorem, is we don't know, and this sounds silly maybe, but we don't know that this is the Taylor series for this centered at 1. We know that this is a power series centered at 1 that equals this. Oh, and this is for all x also, because this was for all x, and no matter what you put in for x here, you just get a number, so this is for all x. But I'll say it again, it's a slightly subtle point. We don't know that this is the Taylor series for this function centered at 1. It's a power series centered at 1 that equals that function. We don't know that power series representations, once you pick a center, we don't know that they're unique, that if there's one, there's only one. It's true, but we don't technically have a result that tells us that that's true yet. Let me do one more example of substituting, or actually 2 more examples of substituting into series. So that example was particularly easy because the series converged, the original series for e to the x, that equality held for all x. The example I want to look at now, I want to look at the fundamental geometric series, this one, which we know is true. This is for the absolute value of x between less than 1, so it's for x between minus 1 and 1. But now I want to look at 1 over 1 plus 3 times x plus 2. Okay, so this means, well, you just do the same thing. X here was a number. Now, it had to be between minus 1 and 1. So we're going to substitute in minus 3 times x plus 2 for x here in this series and into the condition, right? Whatever we put in here for x has to be between minus 1 and 1 for this to hold. So when I replace this x by the quantity minus 3 times x plus 2, so that becomes this, I have to put it in for x every place, including in the condition. So you get a new interval of well, equality, and it's actually of convergence, but again, that's a subtle point that we won't really know until we know that power series representations are unique. So what do we get? Well, you replace x by minus, right, let me write this as it's minus this. So we're replacing the x by that quantity. So you get minus 3 times x plus 2. Then you get this squared, so that's plus a 3 squared times x plus 2 squared. And then you get a minus 3 cubed. Minus 3 cubed times x plus 2 cubed, and so on. This is for minus 1 less than, and now minus 3 times x plus 2 is less than 1. So when this is true, now you can work with inequalities if you want and write this so that it looks like an interval centered at minus 2, where this series is centered. It's a power series centered at negative 2. And we'd like for this to be written as clearly as some interval centered at minus 2. It means we need to divide by minus 3. Remember, dividing by a negative number reverses inequalities. So if you divide by minus 3, you'll get 1/3 is greater than x plus 2 is greater than negative 1/3, or I don't know, I like writing it the other way. It's negative 1/3 is less than x plus 2 is less than 1/3. So, yeah, or you could write the absolute value of x plus 2 is less than 1/3. So it's an interval of radius 1/3 centered at minus 2. And we know that this equals this on that interval. I'll say it again. We don't technically know, except I keep saying it, that if we found the Taylor series for this centered at minus 2, that this would be what it is. But it's true. It's true. And one more example of substituting in. You can play this game with lots of functions, and it's nice. You start with kind of Maclaurin series that you've memorized, and you just mess with them to get other things, although we're going to mess with this one and get a function we're familiar with, but centered at an unusual place. So let's take the Maclaurin series for cosine. You're supposed to have this memorized. It kind of looks like the e to the x one, but you only get the even powers, and the sign alternates. Great. What do I want to do? I'm going to substitute. I'm going to replace the x by the quantity pi over 2, or x minus pi over 2. Now, it's a trig identity that this is equal to the sine of x. That's no problem. But if you replace the x by the quantity x minus pi over 2 here, oh, I should have said this was for all x. You get 1 minus x minus pi over 2 squared over 2 factorial plus x minus pi over 2 to the 4th over 4 factorial, and so on. So what you get with essentially zero work is, and again, this is for all x, because no matter what x is, x minus pi over 2 is just some number, so this is for all x. So what you get with no work, really, I mean, you had this memorized. Suppose you want a power series centered at pi over 2 that equals sine of x. Well, just substitute in x minus pi over 2 into this, and you get that sine of x equals this. I've said it twice before, I'll say it again. We don't technically know that this is the Taylor series for sine of x centered at pi over 2. Well, I say that except we did it in an earlier section, but just from this work, we don't know that. You can do the calculation and see that it's the same, but in just a minute, we're going to have a general theorem that tells us, yeah, if a function equals a power series centered someplace, then it's the Taylor series. Okay, so let's do that now. I'm not going to prove any of the things that we do today, except maybe easy corollaries of bigger things. This really is a section on manipulating power series, and it's the beauty of it is that it's so easy and gives you so many nice things so quickly without having to calculate a lot of Taylor series or Maclaurin series, without having to prove things on errors. On error terms, you just work with known things and manipulate them and get new things. So it's really very cool. So what's the theorem that's going to tell us that power series representations are unique? Well, it may not be obvious, but that follows as a corollary to how you differentiate power series. So it's a theorem. Suppose P of x is a power series centered somewhere. So we've got some power series centered at A. And let's say it has, suppose P of x has radius of convergence, R. then what? The new series that you get by taking term-by-term derivatives of this. So by that, I mean, if this were a big polynomial, that's a constant. That's some exponent. There's an x, there's a constant. The derivative of this with respect to x, you would just use the power rule and get ck times k times x minus a to the k minus 1. Yeah, by the chain rule, you should multiply times the derivative of x minus a, but that's just 1. So the term-by-term derivative, oh yeah, and the constant term, when k is 0, when you differentiate, that goes away. So this new series will start at k equals 1. But the term-by-term derivative function. So here's what we get if we did the power rule to each term. And that's what you do for a polynomial. You just differentiate each term and then add them together. And the whole point is that infinite, or the power series, even if they're infinite, behave like never-ending polynomials. Then this has radius of convergence r, and on the open interval from a minus r to a plus r. So this series has radius of convergence r, and it's centered at a, so it at least converges here. It might also converge at the endpoints. This series, we're saying, has the same radius of convergence, so it converges at least here, and it may converge at the endpoints. But the point is that that term-by-term derivative is, in fact, the derivative. So what does this say? It says on the open interval of convergence, so in the interior of the radius in the interior of the interval of convergence, you differentiate power series as though they're big polynomials. If this had radius of convergence 0, then there's not anything to differentiate, really. That just means you're saying you've defined a function at a point. That's not very interesting. So, of course, the interesting case is where the radius of convergence is greater than 0, and then this says you differentiate like it's a big polynomial. Why does this give us as a corollary that power series representations of functions are unique? This is easiest to see if I write out the power series. So yes, I could do this in gory summation notation and with induction, but let me write out the power series. C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed. I want one more, just so we have enough terms to see what's going on. X minus a to the 4th plus dot, dot, dot. And I'm going to assume the radius of convergence r is positive so that we're doing something good. And start differentiating. What that theorem says is, yes, if you take this function, it's differentiable. Oh, I never said that explicitly. The fact that I wrote that the derivative equaled that thing and the radius of convergence of that thing was the same means, in fact, that the derivative exists, so the function's differentiable. So p prime of x is c1. So you get a z. Oh, let me put things under where they belong. Plus a 2c2 times x minus a plus a 3c3 times x minus a squared plus a 4c4 times x minus a cubed, and so on. All right, well then what's p double prime? Now this is a function. It equals this with the same radius of convergence. You can differentiate again. Right? The same theorem tells you, oh, yeah, then this is differentiable. It has the same radius of convergence after you do the term-by-term derivative. So you get a 0 plus a 2c2 plus a 3 times 2 times c3 times x minus a plus a 4 times 3 times c4 times x minus a squared plus, and so on. You can differentiate a third time. And this is the last time. I won't do this again, but this should be enough for you to see. We can keep going. We can just keep differentiating. You get 0 plus 3 times 2 times c3 plus 4 times 3 times 2 times c4 times x minus a plus, and it keeps going. What is the point of my writing out all of this? It's that in each of these, you can plug in x equals a. The only place where we really know easily how to evaluate power series at the center. But if you do that, what you find is that if I plug in a here, I get p of a equals c naught. I get p prime, if I plug in a here, I get p prime at a equals, all those terms go away, equals c1. If I plug in a here, I get p double prime at a equals, all of these terms are 0, but I'm left with 2c2. If I plug in a into this last one, I get 3 times 2 times c3, and then all zeros. If you divide by these constants, you find that this differentiability theorem is telling us that you get the coefficients in the Taylor way. C naught is p of a. C1 has to be p prime of a. C2 has to be p double prime of a over 2. C3 has to be p triple prime of a over 3 times 2, which is 3 factorial. In general, you will get that the kth term has to be the kth derivative of p evaluated at a divided by k factorial. But those are the Taylor coefficients. Those are the coefficients in the Taylor series for p of x. And so the corollary of this differentiability theorem is, the corollary if p of x equals a power series. Now, I've said this a bunch of times now, but now we know it's true. Corollary, if p of x equals a power series centered at a, if this has radius of convergence greater than 0, then the power series has to be the Taylor series centered at a. So a lot of people phrase this as power series representations of functions are unique. They mean unique after you specify the center, and of course they mean on an interval of convergence that doesn't just consist of the center, because that's just dumb. You've got a function defined at a single point. Yeah, power series representations of functions are unique, so that if a function equals its a power series, that power series has to be the Taylor series, which is what I said several times. You should understand how much work this saves you. Or maybe before I say that, maybe before I do another example, I should say that this generalizes something you should have been told, should have had emphasized to you in high school, that if two polynomials define the same function, it may have been unclear exactly what they were saying in high school. Maybe I can make it more clear, maybe not. If you've got two polynomials that are equal for all x, so that define the same function, then you should have been told in high school that happens if and only if the coefficients of the polynomials are the same. By there they mean polynomials that were centered at 0, so just powers of like x, and they meant the polynomial functions. If the polynomial functions are equal, which means they're equal for all x, then the coefficients have to be the same. They weren't, so if you want to do this in in our terminology, or terminology we could use, if the polynomial functions are equal, the formal algebraic polynomials, meaning the algebraic expressions, so have to be the same. So that just means the coefficients are the same. This theorem, this corollary says the same thing. If you've got two power series representations, both centered at A, and they're equal on some positive or some interval, some open interval containing A, so on some interval around A that has a positive radius, then the coefficients have to be the same. So if you've got two infinite series, both centered at A, and they're equal as functions on some open intervals around A, then the coefficients have to be the same. So power series representations are unique. This can save you a lot of work. So, for instance, we'll go back to our friend e to the x. E to the x equals x 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And just by substituting, so that's for all x, I won't bother writing it, we can replace the x by x squared, that's fine. This does not take a theorem. If x is some number, x squared is just some number, and we can certainly put it in for x up there, not a problem. But before we had this corollary, we didn't technically know that this is the Maclaurin series for this. It has to be. This equals this power series centered at 0, so it has to be. It's Maclaurin series. You might go, you might think, yeah, how does that save us a lot of work? Suppose you started with this function and had to calculate its Maclaurin series barehandedly, so just from the definition, which means you need all the derivatives of this evaluated at 0. Well, the derivatives of this are a pain to calculate. You do the chain rule, so you get e to the x squared, but then you get a times 2x back. Then you want the second derivative, so put it here. So you can pull out the constant 2, but then you still have to do the product rule. The first thing times the derivative of the second plus the second thing times the derivative of the first. So we get an e to the x squared times 2x. And you can factor out the e to the x squared if you want to. E to the x squared times 1 plus 2x squared. And then you keep going. F triple prime. Again, you can pull out the 2. And then you'll have to do the product rule again. It's the first thing times the derivative of the second. I feel like I'm messing up. Plus the first thing times the derivative of the second. Plus this second thing times the derivative of the first. So times an e to the x squared times 2x. And you can factor out the e to the x squared, and you can keep going. It's fairly painful to write down all the derivatives of this and then evaluate them at 0 and divide by the corresponding factorial and see that you get these coefficients. It means that every other derivative has to give you 0, and anyway, it's ugly. But we don't have to do that. Uniqueness of power series representations tells us that if we have this, then we get this by just substituting, and the reason we know that that's the Maclaurin series of this is because we have the corollary that we just discussed. All right, well, that's the corollary and why it's so important. We've actually I've referred to it many times in the past. How do you use the theorem itself on differentiability? Well, you can differentiate. And it gives you a way of getting more Maclaurin series, more Taylor series for things from known ones. It's true that in the last section I talked about, suppose I define a function by this weird, arbitrary, ugly power series. Can you find the radius of convergence? Yes, but in general, that's not the most common use of all of these techniques. We want things like, we kind of want Maclaurin series and Taylor series of kind of more finitely described things. So let's take the fundamental geometric series. So this one. Which we know is true if the absolute value of x is less than 1. I'm going to differentiate it. Just differentiate. This is 1 minus x to the minus 1. Its derivative by the power rule minus 1 minus x to the minus 2, but then by the chain rule you pick up another minus sign. So if I differentiate this side, I get 1 over 1 minus x squared. And over here, when I differentiate this side, I get 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus, it just keeps going. This is true on the same, at least on the same open interval of convergence. So that interval was already open. I should say that what happens at the endpoints of the interval. You can lose convergence at the endpoints of the interval when you differentiate, but you can't gain it. If the original series didn't converge at the endpoints, this derivative series won't converge at the endpoints. But this was true on the open interval. This is true on the open interval centered at minus 1 of radius 1. Yeah, and this tells the Maclaurin series of this is that. You might notice that this is this squared, and later when we talk about multiplication of two series, it's true that you could multiply this series times itself and also produce this. But multiplication of series is much uglier than differentiation of series, so this is certainly still how you'd want to do it. I don't know, this is kind of cool. If you look at this and this and put in x is a half, for instance, when x is a half, this top thing tells you that 2 is equal to this geometric series. Great. And it's just kind of cool that when you put in a half here, you get you'll get a half squared, so you'll get 4. You get a half squared, so you get a fourth. But 1 over a fourth is 4. And that if you put in a half for each one of these, you get 2 times a half plus 3 times a half squared plus 4 times 1/2 cubed plus 5 times a half to the 4th. I don't know about you, but I just find this, right? A half is inside our intervals of convergence. I just find this kind of cool that, yeah, 2 equals this. So what happens if I multiply this term by 2, 3, 4, 5? I think it's distinctly non-obvious that all that does is square this 2 and give you 4. But this tells us that it's true. So that's kind of nice. All right. Now that we have differentiation of series, anti-differentiation of series, well, that's just the process in reverse. So that's true as well, that you anti-differentiate series by undoing differentiation. So there's an extra thing that happens. With differentiation, you can lose convergence at the endpoints when you differentiate. In integration, you can't lose convergence at the endpoints, but you can gain it. But again, we don't really care so much about what happens at the endpoints, the interval of convergence. I could state this as a careful theorem. It's once again that the radius doesn't change, but let me just write it in terms of formulas. So suppose we have this. So we have a power series. And it defines a function on its interval of convergence. You can ask for an antiderivative of this. So this defines some function on its interval of convergence. It's a continuous function, right? That's Abel's theorem, it's continuous. So we can ask for, actually that would be relevant if we were after a definite integral. I'm just after an indefinite integral. So I'm after some function whose derivative is this one. So I shouldn't have bothered mentioning Abel's theorem. So we want an antiderivative of this. Well, actually, the last theorem on differentiation tells you how to produce an antiderivative. You anti-differentiate term by term. So it's the power rule for integration. You add 1 to the exponent and divide by the new exponent. So you just get ck over k plus 1 times x minus a to the k plus 1. But you can get plus an arbitrary constant out in front. So this is true. And yeah, what I was saying about Abel's theorem, if you want to translate this into a theorem about definite integrals, then you need to use Abel's theorem and know that this definite integral exists because this is a continuous function. And then you can evaluate from one endpoint to another using the fundamental theorem and using that this is an antiderivative. But let's look at the indefinite integral statement, right? Why is this an antiderivative of this? Because we have the differentiation theorem. We know that the derivative of this is in fact that. We don't know the statement about convergence that I made at the endpoints, but it's okay. This and its derivative have the same radius of convergence. Okay, so how would you use this? Well, let's look at that. We found the Maclaurin series for the natural log of 1 plus x, and you can do the error estimate and prove, you can use the Lagrange form of the remainder and prove that the Maclaurin series for natural log of 1 plus x converges to natural log of 1 plus x, provided x is greater than 0 and less than or equal to 1. But we never actually did the part about how do you know that that's the Maclaurin, that the natural log of 1 plus x equals its Maclaurin series when x is between minus 1 and 0. But we can do that easily now. So you start with, you try not to memorize too many things. Once again, you start with our favorite fundamental geometric series. We can replace the x by minus x everywhere. If the absolute value of x is less than 1 and I replace that x by minus x, I get the absolute value of minus x, and the requirement's still that the absolute value of x is less than 1. So if I do that, I replace all the x's by minus x's, I get, when you square the minus x, you get plus x squared, so you get a minus x cubed, a plus x to the 4th, a minus x to the 5th, and so on. And it's still if the absolute value of x is less than 1. But now we can integrate. Or anti-differentiate both sides. The antiderivative over here, x is between minus 1 and 1, so this denominator is positive. So you get the natural log of 1 plus x, you don't need absolute value signs, equals c plus, and you integrate each term like it, as a polynomial. The integral of 1, x, integral of this, you get a minus x squared over 2, you get a plus x cubed over 3, a minus x to the 4th over 4, plus x to the 5th over 5, and so on, minus x to the 6th over 6. And this is certainly true on at least the open interval where the absolute value of x is less than 1, so for x between minus 1 and 1. well, we don't want this big C here, and so we want to figure out the constant. Well, how can we figure out the constant? You plug in the only x value where you know everything, the center, namely 0. We want to figure out that C, plug in x equals 0. When x is 0, you get the natural log of 1 equals C plus, well, a whole bunch, an infinite number of zeros. But the natural log of 1 is 0, so the C itself has to be 0. And this is how you always find these constants when you do these indefinite integrals of power series. You plug in the center. And so you get this. Well, this was the Maclaurin series, what we found before from the Maclaurin series of the natural log of 1 plus x. And we've just derived it very, very quickly. No formulas for the derivative. I mean, we had to know this Maclaurin series. We had to know this equality up here. But then you manipulate that one to get this one. You replace x by negative x, and then you integrate. Notice that this doesn't give us. So what do we get? We get that this is true if x is between minus 1 and 1. We don't get convergence at x. We don't get that this equality holds at x equals 1, which we showed by using the Lagrange form of the remainder earlier. Pretend that we hadn't shown that earlier. How could you conclude it now? Well, you need to know something else, but well, how could we conclude this at 1? If we knew somehow that this converged at 1, so when you put in x as 1, you get the alternating harmonic series. If we knew the alternating harmonic series converged, now the reason we know that is because we proved it equaled natural log of 1 plus x, so we know it equals the natural log of 2. But if we knew that some other way, if we hadn't done that as part of our, here's the Lagrange form of the remainder, if somehow we knew the alternating harmonic series converged, that would mean that the interval of convergence of this included 1. And this is certainly a continuous function. It's continuous when x is 1. And we would apply Abel's theorem and say, well then if these two continuous functions are equal on the open interval from minus 1 to 1, and this one converges at 1, then these two functions are equal at 1. And that's what a lot of books do. We have put off these other tests on convergence, so we don't have a way yet of telling that the alternating harmonic series converges other than our proof using the Lagrange form of the remainder. But we certainly get this theorem on this entire open interval, so it gives us the part we were missing between minus 1 and 0. Okay. Well, let's do one we don't know, or we haven't looked at. Let's look at, once again, start with the fundamental geometric series. Replace the x, now I'm going to replace the x by negative x squared. And so what I'm going to get is 1 over 1 plus x squared. All right, let's not mess this up. You get 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th and so on. Plus x to the 8th. Minus x to the 10th, and so on. This is, I replace the x by minus x squared, so this is if the absolute value of minus x squared is less than 1. Well, the minus sign doesn't matter. And the absolute value of x squared is the absolute value of x squared, and saying that's less than 1 is the same as saying the absolute value of x is less than the square root of 1. So in fact, we just get, once again, if the absolute value of x is less than 1. And now you probably know where I'm going with this. I'm going to anti-differentiate both sides. I'm going to integrate both sides. Over here, you should know, you get the inverse tangent of x equals, and you integrate, you get a big constant, and then you integrate each one of these term by term. So you get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9, and so on. You get odd terms divided by, divided by the corresponding factorial, but just by the single, there are no factorials here. Is this worth memorizing? Probably not. It's so easy to derive it quickly. How to figure out what C is? You plug in x is 0, inverse tan of 0 is 0, all that's 0, so C is once again 0. So here's what we really get. This, you shouldn't bother memorizing. It's so easy to derive. It's, again, this is if the absolute value of x is less than 1. It's also true, let me write that as x between minus 1 and 1. It's also true that the same test for alternating series that would tell us that if we had it, that tells us that the alternating harmonic series converges, would tell us that when we plug in x is 1, we get a convergent series over here to go 1 minus a third plus a fifth minus a seventh. It looks like an alternating harmonic series, but you only have the odd denominators. It's true that later we'll know that that series converges at 1. So when x is 1, this converges. But that means, and this is a continuous function, this is continuous by Abel's theorem. So it's really true that this equality holds when x is between minus 1 and 1, and you can include 1. Also at minus 1, when you put in minus 1, you'll get minus, let me do that. When you put in minus 1, well, let me say this. This is an odd function. You have odd powers. If you put in minus 1, you get the negative of what you get when you put in 1. But it converged when x is 1, so it will converge when x is minus 1. So in fact, you'll get this equality. Also, what's so interesting about this? Well, putting in 1 is kind of interesting. It tells us that the inverse tangent of 1 is 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th, and so on. What's so interesting about that? Well, the inverse tan of 1 is pi over 4. And that means you can get pi from an infinite series. Just multiply both sides of this by pi, and you will get pi is 4 times this kind of alternating odd harmonic series. How useful is this? Like if you're actually trying to approximate pi? Not very, actually. This doesn't converge to pi, or this doesn't converge to pi over 4 very quickly. And by that I mean you have to go out very far to get good accuracy to make it close to pi over 4. But still, theoretically it's true, and if you go out far enough, you can make this arbitrarily accurate. So it is cool in that respect. There are a couple more things I want to say. I haven't said anything about anything much. I haven't done any examples about adding, subtracting, multiplying power series. I'm not going to state these as theorems. They are in the book. It's just that just kind of hides. It makes things look more difficult than they are. The point is, things behave how you would expect. Suppose you want, let's see, to match with the book, I want 5 sine plus 3x cosine. Suppose I want a Maclaurin series for this. 5 times the sine of x plus 3x times the cosine of x. Oh my God. How do you find one? And the point is, you multiply by scalars like you would expect. You multiply even by x as you would expect. You treat these like they're infinite polynomials. And so I'll just write this with the dots. You could, of course, write the summation formulas. But sine of x, it has the odd powers of x, and they alternate. You have the corresponding factorial. And then there's plus 3x times the cosine terms, so the even powers of x, and they alternate. They're divided by the corresponding factorial. And the point is, yeah, you can distribute this 5, and you can distribute this 3x, and the x bumps up the powers of x over here, and you add them like they're big polynomials and regroup like they're big polynomials. So you multiply by 3x. Let me just do this easily. So you get, distribute the 5, you get 5, 5, 5. Multiplied by 3x, so we get each term multiplied by 3x. So minus 3, and then this would be an x cubed, and a plus 3 times x to the 5th, and a minus 3 times x to the 7th. And then you add the corresponding powers. So you would get, I'm going to leave it split. Yes, I know 5 plus 3 is 8. I'm going to leave it as, just so you can see where it comes from, as 5 plus 3 times x. Then there'd be a plus, I'm going to write plus negative 5 over 3 factorial minus 3 over 2 factorial times x cubed, and then plus a 5 over 5 factorial plus a 3 over 4 factorial times x to the 5th, and so on, plus, I guess I'll do one more, plus a minus 5 over 7 factorial minus 3 over 6 factorial times x to the 7th, and so on. The real point is, don't get upset that you're working with these never-ending polynomials. They just work like polynomials. They just don't stop. It might be a little worse looking in summation notation. Maybe you'd have some issues working with it. But certainly if you write out the plus dot dot dots, it makes it clear what's going on. There's a, I guess I want to do one more manipulation before I say that. Let's do something that looks slightly different, but really it's more of the same philosophy, that you just treat these like they're infinite polynomials. Let's calculate a limit without L'Hopital's rule. So let's take the limit as x approaches 0 of e to the x minus 1 minus x over x squared. Now, when you plug in x equals 0, you get 0 over 0. And we could use L'Hopital's rule and take the derivative of the numerator and divide by the derivative of the denominator. Then we'll get 0 over 0 again. And we could use L'Hopital's rule, and then we'd be finished. And we could certainly do that, but I'd like to do this with power series just to let you know how easy these things are. And we know, or you're supposed to know, there's some Maclaurin series that you're supposed to know. And e to the x equals its Maclaurin series, and it looks like this. Well, then e to the x minus 1 minus x, we'll just subtract 1 and x from both sides. Minus 1 minus x equals this. Okay, great. And what happens when you divide by x squared? All right, now you need x is not 0. But as long as x isn't 0, here you'll get x cubed divided by x squared. And here you'll get, x squared divided by x squared. X cubed divided by x squared, you get an x. And you get higher powers of x over here. You get this. That's if x is unequal to 0, but power series are continuous on their intervals of convergence. If you take the limit as x approaches 0 of this side, you just get what you get when you plug in x is 0, and that's a half. So you get that this is a half. And in a way, this is a lot more intuitive than L'Hopital's rule. Why should this limit be a half? You could use L'Hopital's rule 2 or 3 times in various problems and then get some answer, and you kind of, yeah, but what is that telling me other than that limit? And what you can see that it's telling you is it's picking up this coefficient in the Maclaurin series of e to the x. It's just picking up This 1 over 2 factorial right here, and that's why that limit is a half. Okay, I want to do one very important, very cool thing. It's cheating, even though I haven't done any proofs of anything other than kind of the corollary to the differentiability thing. We're going to have to leave even the things that are proved in the book at this point. We have to believe that calculus works fine with complex numbers, so we're going to allow the square root of -1 in our calculations, I. Most people call it I, electrical engineers call it J, but we'll call it I. We're going to believe that all this infinite series stuff, all the calculus that we've talked about, is true with complex numbers because it gives us something very important. And calculus is true with complex numbers. This isn't a course in complex calculus or complex analysis, which is what it's normally called. But we're going to assume it. So we're going to allow ourselves to use I, which is the square root of -1. So this means that I squared is -1. If you multiply both sides of this by I, it means that I cubed is -I. If you multiply both sides of that by I, you get I to the 4th is -I squared, but I squared is -1, so minus -1, this is 1. And then it starts over. You multiply by I again, you get I to the 5th is I, and then of course the pattern just repeats. You get I to the 6th is -1. So the powers of I, you get I -1 minus I 1, I minus I, it always goes I -1 minus I 1. So what does this have to do with anything? Let's look at our series for e to the x. But now I'm going to put in z's. Z seems to be the favorite variable name in complex numbers. So I am telling you that it's true that you can put in a complex number, a plus b times I, for z, and that this is still correct. For all complex numbers, z. So everything in the form a real number plus a real number times I. It is standard to now put in that z is I times theta, where theta is real. So we're going to let z be I times theta. And it's not crucial that theta is real, but that's how we're thinking of it, a real number. If you put in z is I times theta, you get e to the I theta equals, and here you'll get I theta plus, this is just substitution after we believe that you can do things with complex numbers. You get I squared over times theta squared over 2 factorial plus I cubed times theta cubed over 3 factorial plus I to the 4th times theta to the 4th over 4 factorial. I actually need some more terms, just so in a minute we'll be able to see better what's going on, plus an I to the 5th times theta to the 5th over 5 factorial. And I'll write one more, plus I to the 6th times theta to the 6th over 6 factorial, and so on. So what? That should be what you're asking yourself. But you now use that we know what the powers of I do. Like I squared is -1, so we get minus. I cubed is just minus I, so you can write this as minus I times theta cubed. I to the 4th is 1 again. I to the 5th, now it just starts over. I to the 5th is I. I to the 6th is -1 again. And it just keeps going. If you separate the parts with I and without I, you'll get the parts without I go 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. And you split off the parts with the I and factor out the I, you get plus I times theta minus, here's an I term, minus theta cubed over 3 factorial plus theta to the 5th, here's an I term, over 5 factorial. And there'd be, if I did the next one, minus theta to the 7th over 7 factorial. This, hopefully, you see exactly what this is. This is the Maclaurin series for cosine of theta. Plus I times, this is the Maclaurin series for sine of theta. Cosine theta plus I sine theta. This is extremely important in many areas of mathematics. E to the I theta equals cosine theta plus I sine theta. This is called Euler's formula. Not Euler, Euler. Euler's formula. It is extremely important. It tells you how to convert, kind of trig function stuff into exponential stuff, or complex exponential stuff into trig stuff, depending on which way you want to go. You can use this to easily prove trig identities. I don't want to say much more about it other than it's extraordinarily important. But one cool thing, and you see this formula in t-shirts sometimes, if you put in theta as pi, you get cosine of pi, and sine of pi is 0, so 0 times I is 0. So you get this. E to the I pi is minus 1, or some people add 1 to both sides. E to the I pi plus 1 is 0. The reason people like this formula so much is they say, look at that. They're like the 5 fundamental numbers in all of math in this one formula. E, pi, I, 1, and 0. E to the I pi plus 1 equals 0, or E to the I pi equals minus 1. It's a cool thing. I don't think you'll find it useful in your day-to-day life, but it sure is cool. That, yeah, why there should be a relation between E and pi is just kind of it's amazing. All right. The last thing I want to say in this section is about multiplying and dividing two series. This is ugly. You don't do it very often. Certainly, the multiplication is not so ugly. The division pretty much is. So these are of limited value, but I will say it anyway. So suppose you want to find Maclaurin series for e to the x times sine of x. It is a theorem that on their open intervals of convergence, so in the interiors of intervals of convergence, you multiply infinite series, power series, like they're big polynomials, but it may not even be clear what that means, so let me just not state a theorem, but do an example that should make it clear. So here's e to the x. We know it's Maclaurin series. It's this. And we know it equals its Maclaurin series. Great. And Maclaurin series for sine of x. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. It is true that you can multiply these, and you just have to be careful with how you write your answer. So, what do you get? You kind of do it a term, you start with the lowest degree terms and work your way up. So, how would you get a constant term here that's not 0? Well, you wouldn't, because the lowest degree term in this product would be if I multiplied this lowest degree term times that lowest degree term. So, the lowest degree term in the product is just going to be x's. There aren't going to be any non-zero constant terms. So yeah, there are no constant terms. I'll put a 0. What about x terms? How could you get powers of x? Well, you can multiply 1 times x, or x times a constant, but there's no constant over there, so you just get a 1 times x. Plus, how could you get x squared terms? So what we're doing is we're multiplying and distributing and recollecting terms all at once. So that's what I'm doing. So we're finished with 1, or finished with x terms. How could you get x squared terms? You could multiply that constant term times the squared term over here. Oh, there's not one. How could you get an x squared term from this. You can multiply this times the next term over here. Aha, there is one. So you get an x squared. How could you get an x squared term from this? Multiply this by a constant term over there, but there isn't one. So you just get an x squared. Fine, we're finished with x squared terms. How can you get x cubed terms? You can multiply that 1 times an x cubed term over here. Aha, there is one. So you get, so let me put parentheses and put an x cubed. So what do you get for x cubed terms? There's a 1 times this. I factor out the x cubed, so I get a minus 1 over 3 factorial. What do I have to multiply x by to get an x cubed term? I would have to multiply it by an x squared term over here, but there's not one, so I don't get anything from that. How do I get an x cubed term from this? I'd have to multiply it times an x term over there. There is one. We get x squared over 2 factorial times x gives us an x cubed. You factor out the x cubed, but the coefficient is plus 1 over 2 factorial. So we pick up this times this gives us an 1 over 2 factorial times x cubed. What do you have to multiply this by to get an x cubed term? A constant term over here, but there's not one. So that's it for x cubed. I'll do one more. Plus an x to the 4th term. How do you do x to the 4th terms? It would be 1 times x to the 4th over there. There's not one. Plus an x times cubed terms over there. Ah, there is a cubed term over here. So you get a minus 1 over 3 factorial. How do you get, so we're finished with that one. How do you get an x to the 4th term from this? You multiply it times an x squared term over there, but there's not one. How do you get an x to the 4th term from this? You'd multiply it by an x term over here. Aha, there is one. Plus a 1 over 3 factorial. Our next thing here would be an x to the 4th over 4 factorial. You'd need to multiply by a constant term there, but there's not one. And you keep going. It's true you can write this in summation notation. It wouldn't be that illuminating if I did. Oh, notice that these cancel out, which is kind of cool. So there is no x to the 4th term after you cancel them. Yeah, you can do this, and it works. And as I said before, you could get a power series for 1 over 1 minus x squared by multiplying the power series for 1 over 1 minus x times itself twice using this process. But it's a lot easier to differentiate. I don't really want to do how you divide two power series. Suppose I've got one power series centered at A, and I want to divide by another power series centered at A. Well, you certainly can't let this one hit 0. It's a theorem that if this has a positive radius of convergence around A, and this has a positive radius of convergence around A, that this quotient, the quotient series has a positive radius of convergence around A. And the nicest way to find the quotient series, so you want to find this, is to multiply by q of x. So multiply by q of x, and then put arbitrary coefficients in the r of x, have them as variables, and do the multiplication process and require that you equal the series p of x and match coefficients and solve. I've never seen anybody, I've never seen that actually come up in something somebody wants to do. I mean, yeah, it could be a homework problem or something. But we do this like when I did the e to the x problem, minus 1 minus x, when we calculated this limit. Yeah, all the terms of that are divisible by x squared, so this doesn't involve, and this isn't much of a power series, it's just got one term in it. That we don't mind doing when you just have one term. This is a horrific process. It's extraordinarily time consuming. Fortunately, well, I shouldn't say it doesn't come up it doesn't come up terribly often, but if you have to do it, that's what I would do. I would let the coefficients in the power series be variables, require the product to equal this, do the product in this by this method, and then you get equations for all your coefficients. We're going to stop here. Those are a bunch of manipulations that you can do with power series. Hopefully it convinces you that working with power series is just like working with big polynomials or never-ending polynomials. It's great. In the next section, what we're going to look at is we're going to combine kind of solving differential equations, which we looked at in Calc 1, really solving differential equations and finding power series solutions to them, which gives you kind of just iteration formulas on the coefficients, and it's kind of a cool use of power series functions. So that's what we'll do next.